This video I'm going to be talking about vector projections. So you know from previous videos that if I have a vector, let's say I call this vector label A, we can split this vector into two components. Okay, and the two components we can split it up into is both the horizontal component as well as the vertical component, where this is your I component and J component. And you know both of these components are perpendicular to each other. Okay, we can always write any vector we have in terms of its perpendicular horizontal vertical component. But let's say I'm feeling a little bit special today, and I don't actually want to write it in terms of the horizontal and vertical component. Okay, I'm going to take the same vector A, and rather than writing it in terms of its horizontal and vertical component, I want to write it in terms of another vector B. Okay, I want to say this is vector B. Okay, and I want to write it in terms of this vector and a vector perpendicular to it. So what do I mean by that? So rather than splitting this vector up into horizontal and vertical component, I'm simply going to write it in terms of the vector parallel to B and the vector perpendicular to this. Okay, so we can clearly see that I want to write it in terms of a vector that's parallel to B, in this case slightly longer than the original orange vector, and the component that's perpendicular to this. Okay, and I'm going to label this as W. Okay, our goal here when we're doing a vector projection is to work out what is the length of this vector here. That is called a vector projection. Okay, so in this case, the vector projection of A onto B. Okay, because we're taking this vector A and we're trying to write it as a component of B. Okay, so we can still see that both these vectors are perpendicular to each other, same like the original example, just in this one it's not horizontal, it's just in the direction of B. To work out this, all we have to do is this is the same as vector A dot producted with vector B divided by vector B dot producted with itself. Okay, and all of this will be a constant. Okay, so we times this, okay, it will become a scalar multiple of vector B. So this vector, what does it tell us? It tells us the length of the entire vector from tail to head. Okay, so this here is the vector projection. So the vector we are working out is this vector in red. So that's how you use a vector projection. And now let us do some questions. Okay, let's start with question 1 here. We are given vector A is this, vector B is this, and let us work out the vector projection of A onto vector B. And the formula for that is A dot B divided by B dot B, and then B. So let's first work out A dot producted with B. So in this case, we can do 1, 3 dot 1, negative 4, and that will simply just give us 1 minus 12, which is minus 11. So on the numerator, we get minus 11. And on the denominator, we can do B dot B. And B dot B, okay, another thing we can do with B dot B is we can say it's the same as the magnitude of vector B whole squared. And the magnitude of vector B is simply the square root of 1 squared plus minus 4 squared. And we can just square that. So that'll just give us 17. And then we can just write vector B next to it. Okay, 1, negative 4. So this is our vector projection. We are saying that the component which is parallel to B, okay, but slightly shorter in this case, okay, is what's going to allow us to have a perpendicular component, like this. Okay, so that's how you work out the vector projection for this set of questions here. Okay, the next one is this one here, another one, vector projection of A onto B. So again, A dot B is what we need to work out first, and that would simply be 1 times 4, okay, plus 3 times 0, which is just 0. So we just get A dot B is the same as 4, and B dot B, okay, that's just the same as the magnitude of B whole squared, which is just 16. And then we can do the scalar projection, the vector projection. So that's the same as 4 over 16, or just 1 over 4, times by vector B, which is 4, 0. So 1/4 in the direction of 4, 0 is how we get the vector projection. The next one is this one here. So 1, 3, and 1, 1. So 1, it's A dot B. Let's work out A dot B first. That's the same as 1 plus 1, 3 times 1, which is just 1 plus 3, which is 4. Then b dot b, that's the same as 2. So if we work it out, we simply just get 4 on 2, or just 2, times by 1, 1. And the last one is the scalar resolute, okay, or the scalar projection. They both mean the same thing. What does a scalar projection mean? Well, if you remember the difference between a scalar and a vector is something which has both a magnitude as well as a direction. So we can clearly see there's a length of this vector here. But a scalar is something which doesn't have a direction. Okay, so something like this, right, we don't know which direction it's going in, would be considered the same as this, okay, because they both have the same magnitude. So in this case, let us analyze the vector projection formula. A dot b divided by b dot b, and then b. Well, what we can really say here, okay, is if we have a look at this equation, we can rewrite this as a dot b divided by the magnitude of b squared, and then b. In other words, we can also say a dot b divided by the magnitude of b, okay, times by b divided by the magnitude of b. So this is what we get. This here, this part of my equation, is what's called a unit vector. Okay, so this is called a unit vector for b. And what is a unit vector? A unit vector, okay, a unit vector is something which has the magnitude of 1, okay, but it's still parallel to your original vector. So for example, if I have vector b, okay, if I have vector b is equal to, let's say, 4 and negative 2, I want to work out a vector, okay, b hat. This symbol denotes a unit vector. I want to work out a vector that's still parallel to this vector, i.e. it's a scalar multiple of this vector, but has a magnitude of 1. Well, the way I do that is I simply just do 1 over the magnitude of the original vector, and then the vector, okay? Or this is also the same as b over magnitude b. They're both the same thing. But let's work it out. In this case, what is the magnitude of b? The magnitude of b is the square root of 4 squared plus minus 2 squared. And that would be the same as square root 20. So 1 over square root 20. And then b, which is 4 negative 2. So this here, okay, we're saying it's still in the direction of this vector because we're only changing the length of the vector. We're not changing the actual direction. But we're saying it's smaller by 1 over square root 20. If the original vector had a magnitude of square root 20, if we times it by 1 over square root 20, would you agree we'll just get a magnitude of 1? So in this case, this part just denotes a unit vector. So let's go back to our equation. We're saying this part here simply denotes the unit vector. Okay, this has a magnitude of 1, so magnitude of 1, okay, but it's in the same direction as the vector of b. But we don't care about the direction. We don't care about this section at all. All we care about is the actual change in magnitude. Okay, and we know this part has a magnitude of 1. Okay, magnitude of 1 times by this is giving us the magnitude of our vector projection. And because in scalar, again, we don't care about the direction, we don't care about this component here because it's just 1 anyway, we can say this here is our scalar projection. Okay, it's our scalar projection, and the reason for that is because this is a scalar quantity. There's no direction associated with it. So if any question asks you to work out the scalar product or scalar projection, okay, that's just the same as a dot b divided by the magnitude of b. So let's go back to this question. Work out the scalar resolute or the scalar projection of a onto b. Okay, in this question, that would simply just be the same as a dot b divided by the magnitude of b. So let's work that out. A dot b in this case, so that's 1 times 1, that's 1. 3 times minus 4, that's minus 12, that's minus 11. Divided by the magnitude of b. And the magnitude of b in this case is simply the square root of 17. So this is the magnitude of your vector projection. Okay, so we don't have any direction or vector quantity, it's simply just a number. So that's how you do scalar and vector resolutes along with unit vectors. Let's have a look at 1 or 2 more problems. Okay, this is our next question. We have two position vectors, so the position of 2 points, 1, 3, and 1, 1, and they're given the label of OA and OB. Find out the vector projection of A onto B, where A is just OA and B is just OB. So let's first do that. The vector projection here would simply be the same as 1, 3, dot producted with 1, 1, divided by 1, 1, dot producted with 1, 1, and then the vector 1, 1. So to work this out, let's dot product the numerator. Numerator, 1 times 1 is 1, 3 times 1 is plus 3, so that's 4, divided by 1 times 1 is 1, 1 times 1 is 1, that gives us 2, and then 1, 1, which again simplifies to just 2 and 1, 1, or you can just write it as 2, 2. That's the vector projection. Now we need to work out, a unit vector. Okay, and the unit vector should supposedly pass through the point of A, but then be perpendicular to the point of OB, or the vector of OB. So to do this, we're just going to use vector projections. Okay, so to do vector projections, let's say this part here is O, and we have this here is vector A, and then we have this here is the point B. I'll draw it even better actually. I'll make it a little bit more steep. So we have point O, okay, and then this is A over here, and then this is part B over here. We know what we just drew, okay, was a perpendicular component as well as an extending component for OB, because these two are now perpendicular. But we just said that the vector projection of A onto B, the vector projection of this onto the floor, was just this entire distance here, okay, and it happened to be 2 times the length of OB. In this case, it's not to scale, but it happened to be 2 times the length of this vector here. Actually, I'll draw it to scale just so it makes a bit more sense. Okay, so this here is what we're saying. We said O to B was initially this, but if we doubled the length, it would give us the vector projection. So now what we want to know is we want to work out a unit vector that passes through OA, but is perpendicular to OB. Wouldn't that just be this vector here? Well, yeah, it would be, right? If it's perpendicular to OB, it would be this vector passing through A. And I'm going to label this vector as W, and I'm going to do it in red. Okay, we want the unit vector of W. Let's first work out what W even is. Okay, to work out W, okay, if W goes in this direction here like that, what we can say is we can say that OA, okay, is the same as the vector projection of OA onto B. And in this case, I'm just going to say that this entire length here is going to be U. It's the same as U plus W. If I want to solve for W, and the reason I can say it's U plus W, by the way, is because to go from here to here is the same as going from here to here, which is just a U, then from here to here, which is just W. Okay, think of it like you're going from, let's say, Perth to Los Angeles. There is no direct flight that goes from Perth to Los Angeles, but what we can do is we can go from Perth to Qatar, and then from Qatar to Los Angeles. Okay, it's the same as going from Perth to Los Angeles though. So anyways, let's continue here. So this is final destination Los Angeles. We can say we can go from Perth to Qatar, and then Qatar to Los Angeles, that's the same as Los Angeles. Okay, anyways, we can say W is the same as OA minus U. And we have both these vectors. The vector of OA is just the same as 1, 3. And the vector of U is the vector projection, which is 2, 2. So that's the same as just 1, negative 1, sorry, and 1. So that's the vector W, which goes in this direction here, which is perpendicular. But we want the unit vector for this here. So what we're actually after is W with a hat on top. Okay, so W with a hat like this. To work it out, we just do 1 over the magnitude of W, and then W. So in this case, 1 over the magnitude of W, in this case, that's the same as square root 1 squared plus minus 1 squared, which is square root 2. So 1 on root 2 times by negative 1, 1. So this here is a unit vector which passes through point A, okay, but is perpendicular to the vector projection we just did. Okay, and that's how you do unit vectors, vector projections, and scalar projections.